Okay, I'm streaming to my other machine, so bear with me while I make sure the audio works. Haven't heard anything coming out of it yet. Oh, there we go. We're good. All right. So, as you can tell, this is the 6th edition of the book. You can use this one. It's fine. I just happen to have a copy of this one. Okay, let me cut the volume down on the other. Technically, I have the 8th edition sitting over here on the shelf, but I also have the 6th edition as well. Just like I was saying in class before, you can pick up these in older editions. They're just fine. So let's buzz through the first half of chapter 1. We could complete it pretty quick. I'm sorry if I'm clearing my throat some, but okay, so here we go. All right, here's the contents. So in chapter 1, basically, we're looking at the properties of fluids. Here he talks a little bit about fluids and what it actually is. He first calls them characteristics. There's two things people confine them to. Some people call them characteristics. Characteristics could include motion and things like that, which are not necessarily properties, but those are fine points that we won't go into right now. You already have a lecture on dimensions and units and dimensional homogeneity. This is a wonderful table which talks about how, now, here's one of the things you have to realize is this is kind of a misnomer. This should say representation. Here's the thing. Here's why. An FLT system happens pounds, feet, second. Okay, an MLT system is actually kilograms. Okay, now the derived unit over here is slugs, kilograms, second, and meter. Derived unit over here is a Newton. So this is called MLT because it has kilograms, seconds, and meters as its base, a mass, a length, and a time. This one is, all ancient units come from an FLT system. Pound, feet, and second derived unit is the mass. So if you say that this is a system instead of a representation, then that's going to tell me that, okay, a force in an FLT system is a pound, but a force in an MLT system will not be written as a Newton, but will be written as a kilogram, meter, second squared. The whole point is you have a Newton. So here, I'm distracting myself with the volume up too high. I'm going to mute it. Oops, let's mute it over here. Okay, I'm muted over there. So the fact of the matter is, this should be representation. For example, let's go down to pressure. Let's find pressure. Pressure. Okay, pressure. Pressure is written in PSI, pascals, or a Newton per meter squared. It's written that way. It is not written this way. So this in so are they telling me, and if they are, they're telling me incorrectly, that in a system that is SI, you don't write pressure as this? No, that's not the case. This is the representation, not the system. So that word should be changed, but I don't mean to be mean or anything, but SI units, as well as English engineering or British units, represent pressure as a pound per inches squared or a Newton per meter squared. This is the representation. But if you get stuck in there and you need to change back and forth, how do you do it? Well, the answer comes pretty straightforward. Hang on. It comes directly out of the force. F is equal to ma, or a mass, a length over second squared. This is the basis of all transformations on this table and everywhere. If you want to transfer here, what you'll notice is in this column is devoid of F's. And this column is devoid of mass. So if you need to get rid of a mass and get a force in there, you have to do through this equation. F is equal to ma, the basis of modern engineering and physics. So just realize that. Another one's like mass, okay? So here's the reverse of, if you have a mass and you want to change it to a force representation, you go this way. Length is a length, but every time you see a force in one, it gets changed out through either this. Here, let me make this a little bit clearer. F is equal to ma is this. But guess what? F is equal to ma is also this, but what you did is you moved the length and the time over to the other side. These are exactly opposite. If you have a force over here, you want to get rid of it, you replace it with this. If you have a mass over here, you want to get rid of it, you replace it with this. It's that simple. I hope that makes sense to you. But none of these columns, everything here has an F, an L, and a T, no M's. Everything here has an M, a L, or a T, and no F's. So units play a big role in fluids. They play a big role in everything. But so we'll go on. As we go on, he talks about systems of units, whether you want to use the SI or whether you want to use the British gravitational. Now, you'll notice in here, his mass is represented as slugs. Here's a thing. Let's see, I've never looked at this. The earliest units, Egyptian cubit, first used around 3000 BC, defined as the length of the arm from the elbow to the extended fingertips. Well, everybody grows up different height, but maybe back 3,000 years ago, everybody was the same height. That's what I figure. So they could run around the marketplace using stuff like that. So this breaks down some more information there. English engineering. Oh, here's the dreaded G sub C. Oh my God. So this is thermo. So if you don't know what to do and you don't want that, you just list this being a pound mass, this being a pound force, and you generate some weirdo kind of unit there to get it, or how should I say, a constant of, okay, so he calls it a constant of proportionality. Okay, that makes my mind hurt. So, but what you notice is if you put it in there, your G sub C cancels all the units out. Here's what I mean. you take a look at this. So your whole goal is to make the whole equation kind of unitless. So if you put a pound force, I'm just looking at the units here, not any numbers. You put in a mass, a pound mass, and you put in acceleration, feet, and what I'm going to do is I'm going to say second to the minus 2. So, and then I'm going to list the G sub C. Now, G sub C can be considered, okay, I have to go to the page of the next page. Okay, so a G sub C could be considered, I don't think I can do this way. Pound mass, a foot, a second to the minus 2, and then a pound. Now, see, he technically should put an F there. Pound F, oops, to the minus 1. Now, shoot, I should carry that over here. Let's see. So what I have is a pound mass. I'm copying this to over here. You can see he doesn't let me, I mean, I could try to copy it. Will it allow me to do that? Copy. Ooh, that's weird. I don't know what I'm looking at there. Here. Get rid of that, get rid of that, get rid of that, get rid of all this. Let's try this again. Ooh, I'm going to do a copy. Go back to the previous page. And I'm going to see if luck will have it if I can just put it somewhere here. Uh-oh. The answer is, oh yes, here we go. So here. Got that stupid pound mass in the way. Well, here we go. All right, now I can get back in here. So if you look at this real quick, okay, so I copied this from the previous page. And now I'm going to use the blue to kind of slice everything. Okay, I got to hit the escape key. Okay, I can hit this, cancel that, and I can have this, which will be pounds force on top, and the units cancel. So the fact of the matter is they made this G sub C such that the left-hand side equals the right-hand side. I just hate dealing with G sub C. Okay, so let's go on. Fluid behavior. Okay, that's great. Fluid behaves. But here we go. Measures of fluids and weights. Density, big deal. Back in thermo, you had specific volume, which was the volume per unit mass. Okay, so a lot of times you had cubic foot per pound mass, or maybe you had meters to the cube per kilogram. Turns out the density is the upside down or the reciprocal of that. Density is generally, and this came from this, PV equal RT, or P equals to rho RT. That's the most common form, I guess, in thermo, but in physics you might see it like that. So in fact, if you go look at the tables, and I challenge you to go look at saturated liquid, and then go look at the values of density in the tables in this book, and you'll find a exact reciprocal relationship between the two. And so it says this property is not commonly used in fluid mechanics, but it's used in thermo. So yeah, he's basically told you that, yeah, specific volume. And, I don't know the history behind that. There probably is some reasonable history, but probably deals with the fact that as you get into steam, this is my guess, don't quote me on this, but as you get to steam, if you look at the volume occupied by a certain mass, that number becomes, large, say 1,000 or more, maybe even more than that. But if you're looking at density, that makes it 0.0001, so, or something like that. So you get very small numbers, and you're apt to start dropping digits, but you're not apt to drop digits along here. So it could be that maybe that was the reason. I don't know. If you want to know more about why you think that is, ask Dr. Crone. So here you go. You're looking at water. Water has an interesting behavior in that, and it's really minor, but it sometimes is major. If you've ever heard of a lake turning over, this is possibly one concept. The density reaches a maximum. Okay, this is in SI, of course, and this is the basis of how they decided what this should be. At 4 degrees, it runs at around 1,000 kilogram per cubic meter. You get a little colder than that, you know, you're running back to say 4 degrees C. I'm sorry, 3 degrees C or something like that. It starts dropping down below 1,000. Up here, it picks up, you know, it drops quite a bit. Back here, it doesn't drop as much, but it drops quite a bit up here. So here's the thing. I mean, I've heard people describe this way, and that this is the case. Let's say you had a 1 degree C piece of water attaching itself to right next to a 6 degrees C of water, or maybe 5. Now, what'll happen is, you know, this one being a little bit more hotter than that one will push, well, I don't want to say push, it will transfer some of its heat over, and it'll rise that up. So maybe it'll rise that up to about 4, and maybe this up to about 4. So maybe it should be 6. Anyway, so the key is this. You bring this piece of water together with this piece of water. The reason they can sit next to each other is because actually they have the same density. So when they sit next to each other, they transfer heat from one to the other, and they both move in that direction. When they both move in that direction, they've become a larger group of water, and therefore became a little heavier and start dropping. And so these currents that can happen due to buoyancy like that can start these circulations in fluids. For example, you've seen it. If you're heating the bottom of water, it becomes more buoyant. It comes to the top because it became lighter. Why? Because it got more heat, or generally, you know, something like that. So in effect, cold water can start rotating around, and movements in the water can turn a lake over and create some interesting behaviors. Let me kind of zoom back out. So this is a kind of a weird discussion, but you can find on the inside cover and on the front cover. I don't have a copy of the front cover, except I go to the very, very back of this book, and if I go there, I get out of sequence. So I might go there near the end of the lecture. So we're only 17 minutes in. So the specific weight. Okay, now this is something, okay, so you have specific volume, but is not used here. You have density that is used here, and then you have something new called specific weight, and then you've got something called specific gravity. What is specific weight? It's the weight in pounds per certain volume. If you're looking at water and you take an aquarium, and it's a 1 by 1 by 1 aquarium, you're generally going to be at about roughly 64.4 pounds per cubic foot. So that's a 64, if that's a 1 by 1 by 1, it's a 64 pound group of water. It's hard to keep it stable and carry it around unless you have a lid that it's like completely sealed. You're going to have to be careful that the water wouldn't slosh out on you. But how does it end up that way? Well, if you've got 1.94 slugs per cubic foot, and that's generally accepted density of water times 32.2 pounds per foot. Okay, feet per second squared. Then you get about 64 and change, but you get it in pounds per cubic foot. How does that work? Okay, let's see. Let me dance over to the other page, get a new page, and again, okay, let's go back to it. This is the symbol, rho G. I can write easier here. 1.94 slugs per cubic foot times G, 32.2 feet second squared. So if you actually do multiply these, let's see if I've got the calculator up somewhere. Okay, 1.94, I think I typed it in, times 32.2, 62.4. So, okay, so 62.4, if I multiplied that right, I'm sorry, that's the correct value. But wait a minute. How does this work? Because if you look here, you get a slug, and you knocked off a foot there, but let's leave that foot there. Leave the foot there. And then leave that. Now, how does that relate to a pound cubic foot? Now, wait a minute. On the left, let's see if I've got this right. I got a slug and I got a pound. That's not going to go well until you realize a pound is equal to a slug. I'm just looking at the units here. Acceleration of foot, and I guess I could take the -2. So if I want to, I can take this and do a slug is equal to a pound, and then take a foot -1 and a slug squared. So I took these two, took them to the other side, and I end up with that. So I can take this and put it in here, and then I end up with a pound. Okay, so I'm replacing the slug with this. Pound, foot to the -1, slug squared, foot to the third, foot right here, and then second squared. Bam, 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 bam. What I'm left with is pounds per cubic foot. Typical example of using F is equal to MA to eliminate in this case, I'm eliminating the slugs and I want to replace it with a pound. How do I do it? F is equal to MA. That's how you do it. Okay. And so I was kind of cramped in there. So yes, I made a mistake. I didn't remember that right. It was 62.4. But the key is, this is the weight per unit volume. This is the density per unit volume. Now, all over the earth, everywhere is water. So here's what they came up with. They said, if it's 2 times heavier in water, why don't we just come up with a term that says 2? What do we call it? Well, let's call it specific gravity. Well, wait a minute. It has nothing to do with necessarily gravity and nothing to do with specific. I don't know. Who cares? Someone came up with it. So what you see here is the density in the relationship. So at 4 degrees centigrade, that's your density. At 4 degrees centigrade, that's your density. Now you can obviously see he didn't use any other units except these two, so these are the ones he loves throughout this book. This puts you in communication with other countries. This makes you kind of communicate with people around here and in England, I guess, which I think England's going to more of SI as well. So specific gravity, what does that mean? Something weighs less than, for example, oil. Oil, for example, if you put oil and mix it with water, it won't mix. The oil kind of floats on the top. So here's your oil, there's your water. Well, that obviously means that this oil is lighter. So the specific gravity of oil is less than 1. Now, let's say we took liquid mercury, or mercury which is liquid. You pour it in there, it sits along the bottom, so the catfish can eat it. Then you can eat the catfish, and then you gain weight. I'm making that up, but maybe that's what's happening to you. So here's your mercury. So guess what? Specific gravity of mercury, since it sinks to the bottom, it has to be greater than 1. And it turns out it's like 13.6 or 13.56. So it's either 5.6 or 6.5, I can't remember. So that's when I just use the value of 6, because that's a pretty good. So 13.6 times heavier than water, meaning that if you grabbed it and put it in a cube as a 1 by 1 by 1 cube, and you filled it with mercury, the weight of the thing would be equal to gamma times the volume, because this is the weight per unit volume. Well, if it's 13 times heavier, then 62.4 pounds per cubic foot. That's what it would weigh if it was water. But it's 13.6 times heavier times a 1 cubic foot. How much does 1 cubic foot of mercury weigh? Let's see. 62.4 times 13.6, 848 pounds. So it would be 848 pounds to put that in a 1 by 1 by 1. So there's your weight. So guess what? I can't lift that, so I'm not going to go find mercury. Okay, so he did that. All right, so it's 13.55. Okay, so anyway, close enough. So he did this in density. Okay, now you can turn around and do this. Okay, so here's the deal. Okay, the gamma of some object is equal to the gamma of water times the specific gravity of the object. But the gamma is equal to rho of the object times G, which is equal to rho of water times G times the specific gravity of the object. So guess what you can do? This G equals to that G. So in fact, both these relationships hold. And you can basically knock the G out of both and you get the same thing. This is in density, like he did in the book there. But this is in specific weight, not specific gravity. And so now, ideal gas laws. We're just going to bounce across this real quick. Now this is, like I said before, PV equal RT, or in fluids they like to say this. That's all good. So that's great. That gets you somewhere. And so to the extent that, so here's some of the gas properties in the back and the front covers. So we're not going to do too much in here with compressible stuff. Most of fluids here is going to be incompressible. There is a compressibility thing that you have to deal with when you get to higher speeds of gases, but we don't have time to cover that in here. Viscosity. Viscosity is an interesting property of a fluid, which actually you can see. Normally I would show a video in the classroom, but in the situation in the classroom is kind of similar to this. What he had done is taken an ink and dropped it and pulled it out, and the flow was going from right to left, and it was taking the ink down left. But what you notice is the ink that touches the wall doesn't move that much. I have what I think is a good lecture in describing how, and I would go into the blackboard and look at this lecture, which describes the relationship between stress and the velocity gradient. And this is related, what I try to relate in that video, and I would suggest you watch it, is the stress you feel as you drive down the lanes on a super highway and you are changing lanes. As you change lanes, if everyone was required, everyone was driving an automatic driving car, and you were all driving exactly 70 miles per hour, then all you would have to do is turn your head and look, and you would be concerned with this view, and you could switch all the way across the lanes. No stress. If, however, you are in a set of traffic in which you knew this lane's average was maybe 50 miles an hour, this lane's traffic average maybe 60 and maybe 70 and maybe 80, then to move all the way across, then you're going to look, if you know the lane is coming before you, you're going to have stress because this person's going faster, and if you move in front of him, you could get rear-ended. Likewise, if you're coming across here and you're coming across, you're going to have to exchange momentum. This is the key. You are going to have to exchange the momentum with your car to the lane next to you. If you're in the 80 mile an hour lane and you move here, you will immediately have to put on your brakes or slow down, maybe not immediately, but to 70 in order to fit the speed of that lane. That's going to produce stress in your body because compared to the other one, there's no stress. You can go back and forth across the lanes. People can drive left and right up and down the highway if they're all going exactly the same speed. What does that mean? That means there is a velocity gradient in the flow that here's your stress, and it is proportional to the velocity gradient with respect to y. And believe it or not, they use fluid mechanics in traffic flow in civil engineering. And this is part of, not all of it. That's a much more detailed course than this as far as traffic. This is all I'll talk about here. But that velocity gradient will produce stress in drivers as they shift lanes across a velocity gradient. The other way you can look at it is with the concept of particles in random motion. Two particles in random motion. This one's bouncing around inside of its little sphere. This one's bouncing around inside of its sphere. But if this one's going slower than this one, there's a good chance if they hit each other, this one going slower will slow this one down, and this one hitting this one will speed it up. So there's a stress associated with that gradient. The key is, go back to the book, you will find out as you get down through here, maybe in a page or two. Okay, so here he's talking about how the stress is related to a velocity gradient. It turns out that this relationship generally is a linear relationship. meaning if the velocity gradient doubles, the stress will double. And if this triples, this will triple, and so on and so forth. So the key is this relationship is classified, or he says designated, as a Newtonian fluid. And that's what, okay, most of our world exists with air and water. You got, there's your water, and there's your air, I guess. This is Mickey Mouse, this is H2O, and this is a bunch of hydrogen, not hydrogen, nitrogen, oxygen, things like that, all bouncing around together. So those two fluids, air and water, or I'll use the common term, water, those fit the pattern of, or the definition of, Newtonian fluids. Now, here's some cases like this. Now, what they've done is they've done some experiments, and they found out, well, here's your shearing strain rate, which it's similar to the strain in mechanics and materials, except instead of this being a deflection, it's a velocity. So it's a strain rate instead of just a strain. And so you get the similar relationship. Now you got something like that in, I mean, if you looked at it in mechanics and materials, you might have a material, you might have the strain and the stress, and then the slope would be that modulus of elasticity. Now over here, it's a strain rate and a stress, and the relationship between the two is the viscosity. So viscosity kind of functions in a similar way to modulus here. You can look at it, that's, some people define fluids and structures that way. In other words, they say you take an object, you put it under a strain, if it moves to a certain point and stops under this, or put it under a stress, and you observe whether it moves a bit and stops. If it does and doesn't continue, then it's a solid. If you put it under a stress and it deforms, and then a few seconds later it deforms more, and then a few seconds later it deforms even more, and continues to deform under the same stress, then it's considered a fluid. So, and then they're looking at the strain rate here versus the strain here. And so that's kind of the difference between these two. If you look really close, there's an incredible amount of similarity between these two. And in fact, a lot of the equations down at the differential level are the same. And if you want to get into it further, there's a course called Continuum Mechanics, offered in most or a lot of graduate programs that are dealing with this, and that's the behavior of both fluids and structures in a uniquely common way. So non-Newtonian fluids behave in a weird way. Here's what I mean by that. Here's your strain, shearing strain or strain rate, and here's your stress. So here's something called a Bingham plastic, like toothpaste or ketchup. You put it upside down, it's not moving. If you put water in your ketchup bottle and you turn it upside down, you open the lid, the water is just going to flow out. So under a very small amount of stress, it's going to start flowing. Ketchup, on the other hand, is not. You're going to have to push and squeeze the bottle until, boom, it starts coming out, and then it behaves this way. Pretty common thing. Hang on, my other window went dead. Let me make sure we're still operating. Yep, we're still operating. Make sure I still have sound. Do I have sound? Uh-oh. Did I lose my sound? Oh, wait a minute. Okay. It just paused over here. So getting back to it. The other thing is Newtonian looks straight like this. You can have fluids that under a shear become thicker. And so this becomes, starts out at a low slope and becomes thicker. And then you can have shear thinning, which starts thin and then it starts, or starts thicker and then under the rate becomes thinner. This is the whole area of non-Newtonian fluid mechanics. And I have a lecture that talks about a little bit of that too. Temperature has a variation, or I'm sorry, viscosity can have a variation with temperature. And this is Sutherland's equation. It's used a lot in aerodynamics. As a matter of fact, when I was working in aeronautical field, inside of all the CFD codes, this is a relationship that sits in there to vary viscosity throughout the flow field based upon the temperature that it exists at. And Sutherland's equation is pretty well used and pretty apparent. Compressibility of fluids, we're not going to cover too much of that. And expansion and compression of gases, we're not going to cover that. And speed of sound and Mach number. Vapor pressure. Vapor pressure is the same thing as the saturation pressure. It's basically if you took a bunch of liquid and you pulled a vacuum on it, pretty soon you'll get water boiling. You can get water boiling at room temperature if you put enough vacuum on it so that the boiling temperature drops, or boiling pressure drops down to, say, 80 degrees. So, surface tension is important if you're a bug, and you can see that on, let's see, I'm on page 25. I don't know how to jump. Oh, on page 48. Let's see, how do I do this? Let's do this. If you're a bug, there's what you're interested in. Surface tension keeps you floating along. So I think they're talking about history, and I think at this point, this is chapter 1. So I would say, by all means, okay, this is the equation. So here, the ones you absolutely need to know, this one. However, it can be written also as gamma over gamma of H2O at 4 degrees C. And this one you dealt with earlier. This one, absolute yes. So these three are definite. You've got to know those three to get through here. So those are your three major things. You got to know also what density actually is. And so once you know what density is, you can work your way through here. So the properties essentially are density, specific weight, and specific gravity. Now, I know you had specific volume before, but technically, guess if you think of it that way, you've got specific weight, specific volume, specific gravity, and density, if you still want to think like a thermo person. So next time I'll haul off and work some of the problems out of chapter 1 and try to get us through chapter 1, and then we'll jump into 2 after that. And so I've got 7 minutes left, so I'm going to make use of everything I can. So let me take a few seconds to burrow into just a weird problem. So here you go. You got a piece of plywood. Now before, generally it's 4x8 or 32 square feet. Let's go ahead and say it's 32 square feet. We've got a calculator, we can do it. So we're going to say that it's sitting on top of some sort of fluid here. And so the plywood is sitting there floating on the fluid, and then you decide to come in, here's your plywood, you decide to pull it. So you pull it with, say, 10 pounds, and then you realize you can somehow measure this and say this is 0.001 feet. So how fast does it go? What's the velocity? Let's say it's on water. So I know the density, viscosity of water is 2.34 e to the minus 5. Now you can look this up and you'll see that I think it's around 70 or 80 degrees, somewhere around there. That's the viscosity. The viscosity does change. So then the question is, what is the velocity? You pulled it at 10 pounds. How far did it go? How fast does it go? If you zoom in on it, what you see is you see the top moving along at a velocity. You see it being, what did I say, 0.001 feet deep, and you have a force over it. So if I want, the equation I'm looking at is this. Now this is a force per unit area, or 10 pounds applied over 32 square feet. Now, my viscosity is 2.34 e to the minus 5, and you can look that up. Now, this part, let's get an approximate to that, and I'll say, let's move this to the right. I got 5 more minutes to finish this up, but here, I can go fast because I know you can look this up or rewind it. So the velocity profile here, and this is an important thing that actually does occur on the tip, on the plywood itself, it's moving v. Down here, it's moving v is equal to 0. Turns out that is a linear variation of velocity throughout the laminates or the layers of fluids. So if this were y, and it's supposed to be, and this is v, then what I can do is pick the top minus the bottom. So what you find out is the derivative, or the gradient, is actually nothing more than v over the gap. And that's it. Now, again, you could look at it from another thing. You could pick this being top and this being bottom, and you could say velocity of the top minus velocity of the bottom over the, and this is where your coordinate system starts, you could say. So here's your origin. And so then you could say my y at the bottom, y at the top is g minus y at the bottom is 0. And so I still get velocity, y, because velocity of the bottom was 0, velocity of the top over g. So that being the case, I can just say this is nothing more than 2.34 e to the minus 5 times the velocity of the plywood over the gap between there. Now, I'm not going to claim that it's easy to measure that gap, but these days there's a lot of equipment that you can measure distances pretty accurately. So I'm going to say it's 0.001. 0.001. And now, if you look at this equation, here's what I have as knowns. Okay, so I have on the right side this, I have the left side this. So I go in here and look at it, I get 10 over 32.2 is equal to 2.34 e to the minus 5 times the velocity of the plywood over 0.001, or the velocity of the plywood is equal to, let's see, 10 times 0.001 over 32.2 over 2.34 e to the minus 5. And let's see. Oh, shoot, I went past it. Okay, so I got 10 times 0.001 divided by 32.2 divided by 2.34 e to the minus 5. 13.2, so about 13.2 feet per second. So this is the typical type of stuff that happens that you can use this for. Now, we'll get into more of this later, but the basis of everything here is the shear stress is equal to this times the velocity gradient. And we'll use this on a couple problems here. And this is one typical example of one. So I've got less than a minute, or about 1 minute less. 1 minute or less, and so what we'll do is we'll pick up and work more problems on Friday. And so we're technically done with chapter 1. Remember the homework on this weekend for units, and we'll see you later.